Hi, my name is Abhishek Karmakar, and today in this video I'll be demonstrating my trip project. I've chosen task number one, which is a linear regression problem. It's a supervised machine learning, and here I have to predict the percentage of student based on the number of hours they study. The data set is already provided in the task description, so I've taken that. There are a total of 25 rows present in it, and out of which the first data, which is the first attribute, the hours, it's a float type, and the score is integer type. And there is no null value present in it. Let me tell you earlier this. Alright, so I'll be explaining the whole of the project by cell by cell. So let's just begin. So this is the first cell. Alright. So the first cell, in the first cell, I've mentioned all the libraries. I've imported all the libraries. In the second, I've read the file directly from the link. DF is a data frame. There are a total of 25 rows present in it, and if we look at the info, the two column 0 and 1, the R, there are 25 no null values. It's a float type, and the second is no null of integer type. Here's a statistical distribution, statistical view of the data. Let's suppose we are looking at the R's. There is 25 rows present. The mean is 5, standard deviation is 2.5 around, and the minimum is 1.5. And here's the statistical distribution of the whole data set. Second is again for the score, there is 25 total rows, 51 is the mean, 25 is the standard deviation, the minimum, and here's a statistical distribution of percentage of how the data has been distributed. What I did, it's a transpose of the whole, otherwise it will be appearing like in a column wise, but it has been shown in what's in a row format. Anyways, let's just move on. So here's a pair plot of both the data, both the attributes together. So these column and a row the same, like hours to hours and score to score, and here's the score to hours and hours to score. Pretty much the same thing. Reflection of the diagonal opposite. Okay, so here's the thing. So through this pair plot, we can see how the data are related to each other. And other way, if we want to look and directly not through the data, if we want to have a look at the number, we can see it in the highly correlation like df.core. It shows the correlation between them. So either Pearson or Spearman, either of them has been taken into consideration in the background of this code. Anyways, so the heat map, we can see that 0.98. If we just ignore this diagonal because it's R to R and score to score, that thing will always be 1. Other than that, the column wise, if we see, other than the diagonal, if we see, it's 0.98, which shows it's pretty much correlated. So that is very highly correlated. The null value, there are no null value present, and we can even see that in a seaborne heat map, there's no null values present. But seeing the distribution of the score, so here's the R's versus the percentage score. Here's a score value compared to each R's. So let's divide the data into two parts now, because we have to do the linear regression, so we have to do the prediction. So let's say we have taken X for like in which the model is to be trained, and Y is the output, X is the input, and Y is the dependent output, X is the independent input. So X is R column, whereas Y is a score column. So let's just divide the whole data into training and testing. For training purpose, we have used 80% of the data, which means 25 of 80%, it's 20. And testing, it's 5. Like I've taken 20% of the test data set, like 25, like 5, 20% of the 25 is 5, so 5 has been used for a testing purpose. The random state has been taken for 42, so it won't be affecting much into this unless it's a very high data. Anyways, so we have x train, x test, and y train and y test. So for x train we have y train, and for x test we have y test. So the model is linear regression. So again, from the skdn we have used the linear model and the linear regression. We have imported this function from there, the class from there. So here's the object been created, and it has been fit function has been used for finding out the parameters and then calculating them. The training has been completed now, so I've printed a message after completion of the training. It prints a message that the training is completed. Here's a regression line, the line, so mx plus c, y is equal to mx plus c. So here's the equation. So now if we look at the whole data set, the whole df dot plot, we have found out like the the, the regression line, it quietly highly fits, but we cannot trust totally on it. We need to have some statistical calculations or some error finding correlations from which we can deduce something. So here's the x. x array on which we need to do the y predictions. We need to do the predictions. We have actually the y test, and we will be predicting y prediction, and then we'll be comparing like y test and y prediction. How much less error is it showing? So, anyways, before moving on to the data for the test data, let's have a look for the training result. So, on the training result, the on which the calculations has been made, we can see that this line, it's a quite a good fit, a pretty good fit. So, and for the test, so it's like 25 of 20, with only 5 points red are the test. 1 2 3 4 5, there are 5 red points which the test, and these black, these can you can see these are for like the predicted. So on this line, for each x test, we can see these are the y predictions, and these are the y test. These black are y predictions and red are y test. So we can see the error of how these have been shown. Now if we look at like 30 27, all right, so here's 30 and here's the 27, or you can see 21 27. So 21, this one, which is the actual value, but we have predicted 27 because of this line. 81 83, so 81 is actual, 81 is actual, and 83 is the predicted. This one is 81 and this is 83 predicted. So likewise, so out of the 5 points, so here how much difference has been found? Like these are 2 and there's 3, so there's 6, so there's again 5. So yeah, let's just have a quick found out of, if suppose it's 9.25, something value around over here, it's 9.25, then how much that value will be? It's 92.38, since it's increasing, totally increasing this function, this will be 90 point something, so it's 92.38. So if we need to have a look of are we going in the right direction, for that we have loss functions and we'll be plotting it. So we have used three kind of matrices for this. The first one is a mean absolute error, the second was mean squared error, and third one is root mean squared error. So mean absolute error is 3.9. So it looks like it's a quite a good, like it's a pretty less error, so we can consider it's a good thing that we have achieved less error. But how can we be so sure? So for that, what we did, so here are the three matrices for finding out the error, the loss function, or you can say anything, or the cost functions, whatever you say, whatever you consider, although these have a little different. But for this, we can consider the cost, loss, and the error to be same thing. So what we are doing, we are plotting the residuals. So if we just plot the y prediction, the y test and y pred, and using a bin of 4, so these are automatic. Like I've hard fixed it, but you can just leave it. It will be this one will be automatically, the Seaborn library will be automatically calculating it, but I've used it like a bin of 4. So you would say it's a normal distribution. Now since it's a normal distribution, it's a good sign that the model that we have chosen is a correct choice. Or the histogram, concluding from the histogram of the residuals, it simply depicts that the error beyond some certain values, it's quite less, whereas the central, that's quite high, but it's not that too quite high, but you can see it's 0.0 something the density comes out to be. So since it's a normal distribution, we can pretty much be sure that we are there in a good track. So with that, I conclude my point that here's the model ready. Thank you for giving me an opportunity to work on a grip, and I'm really happy that I've given an opportunity to work on this. Thank you very much. With this, I rest my case.